All right, welcome back. Pre-calculus classes. This is going to be a video that deals with the material on section 4-5 in your textbook. And I wrote the objective up here as just solving equations. And that's all we're going to do. We're going to solve equations. And there are going to be two main types of equations. There are going to be equations that involve exponential expressions, such as 3 to the x equals 11. Okay, that's an equation that involves an exponential expression, so we could call that an exponential equation. That's one of the types of equations we're going to solve today. And then the other type is called a logarithmic equation. And a logarithmic equation is going to involve one or more logarithmic expressions. For example, I could have log base 3 of x equals 12. Okay, and these are obviously both very simple equations, but this is exponential, this is logarithmic. Now, not to spoil the surprise or anything, because everybody already knows from previous sections that exponentiation and a logarithm, and taking the logarithm of something, those are inverse operations. So, to undo exponentiation, like right here, x is being exponentiated to base 3. To undo the exponentiation, we're going to use a logarithm. And then down here, x is having the log to base 3 taken of it. And to undo log base 3, we would use the inverse of log base 3, which would be exponentiation to base 3. So long story short, if you have a variable in the exponent somewhere, and maybe even in more than one exponent, as we'll see, you're going to end up using a logarithm to isolate the variable. And if you have a variable that's inside a logarithmic expression, then you're going to use exponentiation somehow to isolate the variable. Okay, so I have a short list of problems that I'd like to work through here with us, or together with you. And if you want to pause the video and open the 4-5 assignment, the first one I'm going to do is number 4. Okay, so if you go to number 4, of course your numbers will vary, but mine says this. Okay, so I have this written up here, and we are going to attempt to solve this equation. Now, the first thing you can notice is you can think, well, okay, now there are two types of equations in this section, exponential equations and logarithmic equations. You can start to think, well, which type do I have here? Well, I don't see any logarithms, and there is a variable in an exponent, so of course we do have an exponential equation here, which means that a logarithm is going to be involved somehow in solving this. Okay, now, we remember the laws of logarithms from a previous section, and we know that I can use that third law of logarithms a lot of times to bring an exponent down out of the exponent. And of course, what I'm going to do here is to undo this exponentiation to base e. I'm going to take a natural logarithm of this expression right here. I'm going to take a natural logarithm. I'm going to perform that operation on the left-hand side of that equation. Now, to keep things balanced, whatever I do to one side of an equation, I'm going to have to do the same thing to the other side. So I'm going to take the natural log of 7 over here as well. And so I've performed exactly the same operation on both sides of that equation. That means the equation's still balanced. Now, if you need to look back at your third law of logarithms, that'd be fine. But that's what I'm going to use to bring that exponent down and make it a coefficient on that expression. So I'm going to write 0.4x times natural log e equals natural log 7. Now, all of you are well aware of the value of natural log of e. The natural log of e is 1, of course. And so essentially, that natural log e, this is 0.4x times 1. I don't really have to write the times 1. And therefore, that whole expression, natural log e, can kind of just disappear because its value is 1. And now you can see that there's just one simple step left to isolate x. And that's 0.4 times x. To undo multiplication by 0.4, I'm just going to divide by 0.4 on both sides. So again, x is natural log 7 divided by 0.4. Now, if you're on the assignment with me, you're going to notice that there are two answer boxes. The first answer box says find the exact solution in terms of logarithms. Well, this is the exact solution in terms of logarithms. This is the exact solution. There's no real way to improve on that solution. So if you type this in, I mean, you may be able to turn that into a fraction and then invert and multiply. But this form of the answer will be just fine. It is exact. It is perfect. Now, then the second box says use a calculator to find an approximation to the solution rounded to 6 decimal places. Okay, so you've got a calculator. This is one simple calculator entry. I type in natural log 7. I close my parentheses. I divide it by 0.4. And I got 4.864775373. You can round that to 6 decimal places on your own. And we just solved our first exponential equation. Okay, I will erase that and we'll try to choose a more fun problem here. The next one I have written down is number 9. So if you want to scroll down to number 9 in your assignment, I'll write it up here. Now, before we do number 9, and number 9 is going to be another exponential equation. It doesn't really matter what your base is. Okay, let me explain what I mean. If I have like 7 to the 3x equals 12. All right, just because my base is 7 here definitely really in this situation doesn't mean I'm going to want to use base 7 logarithm. To bring that through, to be able to bring that 3x down and make it a coefficient. I'm still going to use a natural logarithm simply because when it gets to the part where we want to get an answer rounded to 6 decimal places, I'm going to want to be able to use that nice handy natural log key that's on my calculator keyboard. So to do a problem like this, and this isn't the one that I was intending to do, but it won't take a second. I take the natural log of both sides, and I get 3x times natural log 7. See, the 3x came out in front there using the third law of logarithms. And over here, I get natural log 12. And then, if you notice, I'm still just one step away from having x isolated. X is being multiplied by 3. It's also being multiplied by natural log 7. So I can divide both sides of the equation by 3 as well as natural log 7. And I get x is natural log 12 divided by 3 natural log 7. That's your exact answer in terms of logarithms right there. Okay, for a decimal approximation, I think you know what to do. All right, now let's go to the one that I intended to do. Again, this is number 9. So I'm going to write this down, e to the 6x plus 3e to the 3x minus 40 equals 0. All right, so this looks significantly more complicated than the first example that we did. And its structure is more complicated. There are now, there are 3 terms on the left side. There's a 0 on the right side. And just maybe take a minute to look at the structure of the expression on the left side. It is a trinomial. Okay, and we've had experiences with trinomials before. Good experiences, bad experiences. This is going to be a good experience, okay, with a trinomial. So if you look at this is e to the 6x, 3 times e to the 3x, and then I have a term that doesn't have, that third term there is just a constant. It doesn't have an exponential component to it at all. Listen, this is structured as though it were a quadratic trinomial. Okay, it's what we call its quadratic in the expression e to the 3x. This first term, e to the 6x, that is the same as e to the 3x squared. Okay, take a minute to make sure you agree with me there. If I raise e to the 3x to the second power, I get e to the 6x because you know the laws of exponents. I have to multiply those two exponents. Then I have plus 3e to the 3x, and then minus 40. Okay, and then you can kind of start to maybe see this come together. I have an expression squared plus 3 times that same expression, and then minus a constant term 40 equals 0. To solve an equation that's structured like a quadratic trinomial. All right, well, quadratic trinomials, if you remember from algebras 1 and 2, have like lots of different methods that you can use to solve them. There's a formula called the quadratic formula. You can complete the square. Or you can try probably the simplest method and see if we can factor this quadratic trinomial. And I'm fairly sure that we can. Let's do this. Let's try to make this e to the 3x plus 8 times e to the 3x minus 5 equals 0. And you can check my work here. E to the 3x times e to the 3x would give me e to the 3x squared, or e to the 6x, so that looks okay. I have plus 8 e to the 3x. I have minus 5 e to the 3x, which if I take positive 8 and take away 5, I think I end up with the plus 3 e to the 3x, and then the 8 times the negative 5 does give me the negative 40. So I think I have this factored correctly. And we all remember, okay, that the whole point of factoring a quadratic trinomial when it's a part of an equation is so that then I can use the zero product property to allow me to set each one of these factors equal to 0. Remember that the product of two expressions can only be 0 if at least one of those expressions is 0. Okay, so either this equation that I have written right here will be true if either this first binomial is 0 or if this second binomial is 0. So I'm actually going to erase the top of this. We'll even erase the section number here. And so I'm going to set this equal. I'm going to write e to the 3x plus 8 equals 0. And then I'm also going to write e to the 3x minus 5 equals 0. Okay, and as you become more experienced and such with these, you'll probably recognize that this first equation right here is not going to take us anywhere that we want to go. If you look at this, I would have to subtract 8 from both sides, so I'd have e to the 3x equals negative 8. And then, the next procedural step, remember, since this is an exponential equation, would be to take the natural log of both sides. So the natural log there, and as soon as you see that natural log of negative 8, you know that this road is not one down which you want to travel. It's not going to get you any solutions, okay? It's impossible for e to the 3x to equal negative 8. Okay, that's not going to get me any solutions. So our only hope, okay, our only remaining hope lies with this second equation. So this looks better. I'll erase this business. And so here I'd be adding 5 to both sides. So I'd have e to the 3x equals positive 5. And that's better, right? That's much better. I can take the natural log of both sides here. I can take the natural log here, and notice this time I have the natural log of a positive number, okay, which is wonderful. The 3x comes out in front here using the third law of logarithms, and then natural log e, of course, is 1. Okay, so the only part of the expression that's going to remain on that left-hand side is just 3x, and over here I'll have natural log 5. If you then divide by 3 on both sides, you will have the exact answer. Okay. Then when I'm looking at that, I look at the box. It says solve the equation, round your answer to 4 decimal places. So I mean, you could type in natural log 5 divided by 3. I think WebAssign would be perfectly happy with that answer. But you could also type this in on your calculator, natural log 5 divided by 3, get a 4 decimal place approximation. WebAssign should be just as happy. Okay. Next one, we're going to number 14. This will be our first logarithmic equation, and it's going to be a great one. I have log, again, this is 14 out of your assignment. So log base 2 of 3 plus log base 2 of x. Okay, and I hope I haven't written this too big here, but I fear that I'm going to have to kind of angle down the page here to fit this. So I'm going to write equals, and we'll start to dive this way. Log base 2 of 5 plus log base 2 of x minus 2. Okay. Teddy, can you look at that and see if, through the screen, does that make any sense at all?
Sort of, if you actually knew what it meant.
Yeah. But I mean, you can read that that's a 2 on the screen, you can.
Yeah, sort of.
Okay. Yeah, I guess I could erase it and write it again, but that would waste your precious time. Okay, so this is a logarithmic equation, and it's got lots and lots of logarithms, right? It's got 2 logarithmic expressions on the left. It also has 2 terms, both of which have logarithmic expressions on the right. So, look, the good news in all of this is that the base for every one of these logarithmic expressions is a 2, okay? So all the logarithms have the same base. That's good. That means I can use the laws of logarithms to kind of maybe combine them into single logarithms. I notice, this expression here on the left, this is not going to be the only way to solve this equation, but what I was thinking about doing was using the first law of logarithms, the product law, to combine these 2 logarithmic expressions into one, which would of course be, and you can look at your first law of logarithms to make sure you agree with me. This would be log base 2 of 3 times x. Okay. So those 2 terms became 1 using the first law of logarithms. Okay, now it looks like I can do something similar over here. I have 2 base 2 logarithms. They're being added. So I think I can write, and again, I'll have to angle here. That would be log base 2 of 5 times the quantity x minus 2. Okay. Now, we're in a good spot here. Because if you notice, I now have just 1 logarithm on the left side. And that's good. I only have 1 logarithm on the right side as well. So it looks like maybe I can just undo those log base 2s and both at the same time, and we'd all be happy. So of course, to undo log base 2, we're going to exponentiate to base 2. So I'm going to exponentiate the entire left side to base 2, and I'll do the same thing to the right side. And of course, exponentiation to base 2 cancels with the log base 2, and I'm left with just 3x. Then over on the right, again, the exponentiation cancels with the log, and I have 5 times quantity x minus 2. And you can see that I now have an equation without a logarithm in sight. Okay, so I can solve this just using old-fashioned algebra. Let's do this. So 3x is 5x minus 10. And let's see, negative 2x is negative 10. And then I'll divide by negative 2 as my final step and get x is positive 5. Okay, and that looks great. Okay, that looks great. Now, I do maybe want to There's no maybe about it. I definitely want to verify that that solution is actually possible. Okay, and what I mean by that is if I substitute that solution value, the 5, back into the original equation, it doesn't cause any issues. And by issues, here's what I mean. Okay, when I substitute the 5 back in here, am I able to take the log base 2 of 5? Well, yeah, 5's positive. It's no problem at all taking the log base 2 of a positive number. It's no problem at all taking the log with any base of a positive number. Okay, over here, I've got log base 2 of 5 minus 2. Well, 5 minus 2 is 3, and 3 is positive, so log base 2 of 3 does exist. It looks like I'm okay here. Okay, so I want you to think strategy here for a minute. And if you're on number 14, you can probably glance at number 15 and realize that, hey, that's another logarithmic equation. I've got more than one logarithm on the left side. I can probably use a law of logarithms to change that fact and make it to where there's one term on the left side. I'm looking at it right now. So the moral of the story is this, okay, strategy-wise. If you have a logarithmic equation, you're going to have to get it to where there's no more than one logarithm on each side, at which point you can use exponentiation to the appropriate base to undo the logarithm. Okay. All right, I think I have one more written down here. Teddy, how are we doing time-wise, boy?
21 minutes, about 22.
Okay. Well, we'll have to make this fast because I'm sure everybody has other things on their plates here. Okay, yeah, so this is going to be an application problem. There are several at the bottom of the page. And the application that we're talking about right here is not one that's unfamiliar to you. So if you want to scroll down to number 19, it's a word problem. It's got some words in it. And it says, it's talking about Nancy. Okay, it says Nancy. She wants to invest $3,000. Or wait, yeah, $3,000. Well, that's what mine says. I don't know what yours says. In savings certificates that bear an interest rate of 9.75% per year, compounded semi-annually. Now, 9.75%, that would be, it would make a lot of people happy, I believe. But then it says, how long a time period should she choose to save? Should she choose in order to save an amount of $4,000? So, in other words, she's got $3,000. She's going to invest it. We want to know how long it's going to take for her to get to $4,000. Well, to get to to solve this, you're going to want to use the compound interest formula. If you have misplaced that, go find it, or you can just wait for me to write it right here. If you've forgotten what all this means, this is your initial amount invested. That's your final amount that you end up with. That's the number 1. R is interest rate as a decimal. N is the number of compounds per year. N up there is also the number of compounds per year. And then the T up there in the exponent is the time period in years. Okay, so this is an the expression on the the right side of the compound interest formula is an exponential expression. It's got a variable in the exponent up there in the form of time. All right, so to solve this, we're looking for how long it's going to take for her to get from $3,000 up to $4,000. So, I think I can fill in some stuff here. I know we want to end up with 4,000. I know that right now we have 3,000. I know that the interest rate it says it's 9.75. So as a decimal, that's 0.0975. And it says it's compounded semi-annually. Okay, that's great. How many times a year is semi-annually, Teddy? If something happens semi-annually, how often does it happen?
3 times.
Incorrect. So semi-annually means twice a year. I don't know what 3 times a year is. It happens twice a year. That means it's going to compound twice over the course of the year. So the number of compounds per year is going to be 2. Of course, that 2 also goes up here. And my unknown is the variable t for time. Now, I need to solve this for time. Time is the only unknown in the equation that I've set up that relates all the givens. If advice here, okay, I probably won't solve this whole thing for you. Start by dividing by 3,000, okay? And then you can take the natural logarithm of each side. You'll be able to bring that exponent out in front to get a variable out of the exponent and eventually solve for the amount of time necessary here. Okay, listen, I'll wrap this up, but I want to, okay, first of all, thanks for watching. If you haven't done 4-4 yet, I checked scores this morning. There's a lot of people with 100%. Seems like everybody's either got 100% or they have not downloaded the 4-4 assignment yet. I know it says the due date's May 7th. Okay, I can bring that forward if it will motivate you. However, I would like to just leave it where it is. But I want you to do it, okay? Because I don't want you to let stuff build up and then, it gets to be May 6th and such. And, you got to do this and that and some other stuff. And, you say, well, can I have an extension? And pretty soon the answer is going to be no, because here's why. In case you don't know, May 8th is going to be the absolute final cutoff date for all this stuff, okay? Now, can I let you go past that? Maybe. But I've got to turn in dual credit grades by May 12th, right? Hear that. May 12th, dual credit grades are going into the computer at Missouri Valley College. So especially if you're a dual credit student, you want to take that into consideration. Thanks for watching. We will see you next time.